The story of the universe begins with one of the most profound and mysterious events ever conceived by science, known as the Big Bang, an unimaginable moment approximately 13.8 billion years ago, when all of space, time, energy, and matter came into existence from a state of infinite density and temperature, referred to as a singularity, a point so small that it defies the laws of classical physics and challenges the limits of human understanding, where the fundamental building blocks of reality were compressed into an infinitesimally tiny volume, before rapidly expanding in a sudden and powerful burst that marked the origin of the cosmos itself, not as an explosion occurring within space, but rather as an expansion of space itself, in every direction simultaneously, causing distances between points in the universe to increase as the fabric of spacetime stretched and evolved, initiating a chain of cosmic events that would eventually lead to the formation of galaxies, stars, planets, and ultimately life as we know it today. During this earliest phase, the universe existed in an extremely hot and dense state, where temperatures exceeded billions of degrees and energy dominated over matter in such a way that particles could not yet form stable structures, instead existing as a chaotic and energetic sea of quantum fluctuations and radiation interacting continuously in ways governed by the fundamental laws of physics. As time progressed even within fractions of a second, the universe began to cool as it expanded, allowing energy to transform into matter through processes described by particle physics, giving rise to the first subatomic particles, such as quarks and leptons, that would later combine to form protons and neutrons, setting the stage for the development of atomic nuclei in subsequent minutes through nuclear fusion reactions in a process known as Big Bang nucleosynthesis, during which the lightest elements, including hydrogen and helium, were produced in vast quantities that would become the primary building materials of stars and galaxies in the future. While the expansion continued relentlessly, driven by the immense energy released at the moment of creation, shaping the large-scale structure of the universe by influencing how matter would eventually cluster under the influence of gravity, forming the cosmic web of filaments and voids observed today through advanced astronomical instruments and space-based observatories operated by organizations such as NASA, which study the remnants of this ancient event through the detection of cosmic microwave background radiation, a faint afterglow of the Big Bang that permeates all of space and provides a snapshot of the universe when it was only about 380,000 years old, revealing tiny fluctuations in temperature that correspond to density variations in the early universe and ultimately gave rise to the formation of galaxies and clusters over billions of years. Theoretical understanding of the Big Bang has also been shaped by the groundbreaking work of scientists like Albert Einstein, whose theory of general relativity describes how mass and energy influence the curvature of space-time, allowing cosmologists to model the expansion of the universe and trace its evolution back to an initial singularity, as well as observational contributions from astronomers such as Edwin Hubble, who discovered that distant galaxies are moving away from us with velocities proportional to their distances, indicating that the universe is expanding and therefore must have been smaller and denser in the past, supporting the Big Bang theory as the most widely accepted explanation for the origin of the cosmos. This expansion continues to this day, shaping the destiny of the universe as it evolves over cosmic timescales, influencing the rate at which galaxies move apart, and determining whether the universe will expand forever or eventually collapse under its own gravity. While modern missions conducted by the ESA and other scientific collaboration continue to refine measurements of cosmic parameters such as the Hubble constant and the density of dark matter and dark energy in order to better understand the conditions that existed at the birth of the universe and the mechanisms that governed its earliest moments. Despite the remarkable progress achieved in observational cosmology, many questions still remain unanswered, including the true nature of the singularity and the physical processes that triggered the Big Bang itself, which may require a unified theory, combining quantum mechanics and gravity, to fully explain. Yet the Big Bang remains the cornerstone of modern cosmology, providing a coherent framework that connects the origin of space and time with the large-scale structure of the universe observed today, illustrating how, from a simple beginning governed by the laws of physics, the vast and complex cosmos emerged through a continuous process of expansion, cooling, and structure formation that ultimately led to the existence of galaxies, stars, planets, and living beings capable of contemplating their own cosmic origins and seeking to understand the fundamental nature of reality itself through scientific inquiry and exploration. In the earliest fraction of a second after the Big Bang, the universe underwent one of the most dramatic and transformative events in its entire history, a phenomenon known as cosmic inflation, a brief but extraordinarily rapid period of exponential expansion during which the size of the universe increased by an incomprehensible factor in far less than a trillionth of a second, stretching from a subatomic scale to something macroscopic in size, smoothing out irregularities and size, setting the foundation for the large-scale structure we observe in the cosmos today. This theory was proposed to solve several major problems in early cosmology, including the horizon problem, the flatness problem, and the monopole problem, each of which challenged the standard Big Bang model by raising questions about why distant regions of the universe appear so uniform in temperature despite being too far apart to have exchanged information at the speed of light, why the geometry of the universe appears so remarkably flat rather than highly curved, and why predicted exotic particles such as magnetic monopoles are not observed in abundance. Inflation elegantly resolves these issues by suggesting that before this rapid expansion, the observable universe was contained within a tiny, causally connected region that allowed energy and temperature to equalize, and then inflation stretched that region beyond observable scales, creating the illusion of uniformity across vast distances, while preserving tiny quantum fluctuations that would later grow into galaxies and clusters. During this inflationary epoch, the energy driving expansion is thought to have been associated with a hypothetical scalar field, often called the inflaton field, whose potential energy dominated the dynamics of space-time and caused gravity to act repulsively rather than attractively, leading to exponential expansion that doubled the size of the universe again and again in fractions of a second, a process so powerful that it effectively ironed out curvature and drove the universe toward spatial flatness, leaving behind a cosmos that appears geometrically balanced on the largest scales, as confirmed by precision measurements of the cosmic microwave background radiation obtained by missions such as those conducted by NASA and ESA, which have mapped tiny temperature variations across the sky, revealing patterns each day consistent with inflationary predictions. These fluctuations are believed to have originated from quantum uncertainty inherent in the vacuum itself, where random microscopic variations were magnified to cosmic proportions by the rapid expansion, becoming the seeds of structure that gravity would later amplify into galaxies and superclusters over billions of years. Inflation also implies that the observable universe may be only a small part of a much larger cosmic expanse, possibly even part of a multiverse in which different regions underwent inflation in slightly different ways, leading to varying physical constants and properties. Although such ideas remain speculative and continue to be explored within theoretical physics, the end of inflation occurred when the inflation field decayed into ordinary particles and radiation in a process known as reheating, filling the universe with a hot, dense plasma that resumed the more gradual expansion described by the traditional Big Bang model, marking the transition from an inflation-dominated epoch to a radiation-dominated epoch, to a radiation-dominated epoch, to a radiation-dominated epoch, and photons interacted intensely in thermal equilibrium. The success of inflationary theory lies not only in its ability to solve conceptual problems, but also in its predictive power, including the near-scale invariant spectrum of density fluctuations observed in the cosmic microwave background, and the absence of large spatial curvature, both of which match observational data with remarkable precision. Yet despite its explanatory strength, inflation is not directly observed but inferred from evidence, and its underlying mechanism remains uncertain because the inflation particle has not been detected in laboratory experiments, prompting physicists to seek connections between inflation and high-energy particle physics theories, such as grand unified theories or string theory, in which additional fields and dimensions may play roles in shaping early cosmic evolution. The concept of rapid expansion is consistent with the framework of general relativity developed by Albert Einstein, whose equations allow for dynamic solutions, in which spacetime itself can expand or contract, depending on energy content. While later observational confirmation of expansion by Edwin Hubble reinforced the idea that the universe has been evolving since its beginning. Cosmic inflation represents the bridge between quantum-scale physics and the large-scale structure of the cosmos, connecting microscopic randomness with macroscopic order in a way that illustrates the profound unity of natural laws across scales. And although scientists continue to refine models and search for signatures such as primordial gravitational waves that could provide direct confirmation, inflation remains one of the most compelling and widely accepted components of modern cosmology, explaining how the universe achieved its observed uniformity, flatness, and structure while emerging from an almost unimaginably tiny and energetic beginning into the vast and intricate cosmos that continues to expand today. As the universe continued to expand and cool following the end of cosmic inflation, it entered a new phase in which the intense energy that once dominated spacetime began to transform into the most basic building blocks of matter, marking the beginning of the formation of fundamental particles that would eventually give rise to atoms, stars, galaxies, and all visible structure in existence. During the first microseconds after the Big Bang, the temperature of the universe remained so extraordinarily high that matter as we know it could not exist in stable forms. Instead, the cosmos was filled with an energetic soup of elementary particles, including quarks, leptons, and gauge bosons, constantly netteracting, annihilating, and reforming in a dense thermal equilibrium, governed by the principles of quantum mechanics and particle physics. These quarks would later combine to form protons and neutrons, while leptons such as electrons would remain as independent particles, essential to atomic structure. In quietain, the interactions among these particles were mediated by the four fundamental forces of nature, including gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, all of which played crucial roles in shaping the behavior and properties of matter. In the earliest instance, it is believed that these forces may have been unified into a single fundamental interaction that separated as the universe cooled, allowing distinct physical laws to emerge and govern particle interactions in new ways. The strong nuclear force became responsible for binding quarks together to form hadrons such as protons and neutrons, while the weak nuclear force enabled processes, like beta decay, that would later influence nuclear reactions inside stars. As the universe cooled below 1 trillion degrees Kelvin, quarks began to combine into stable triplets, forming baryons in a process known as hadronization. This transition marked a significant milestone because it allowed matter to take on more complex and lasting forms. Shortly afterward, a slight imbalance between matter and antimatter resulted in the survival of a small excess of matter that would make up all visible structures in the universe today. This asymmetry remains one of the most intriguing mysteries in modern physics, because theoretical models suggest that matter and antimatter should have been created in equal amounts and annihilated completely. Yet observations confirm that matter dominates the cosmos, implying the existence of processes that favored matter during the earliest moments of cosmic evolution. As protons and neutrons formed, they remained immersed in a hot plasma of photons and electrons constantly interacting through scattering processes that prevented the formation of stable atomic nuclei until the universe cooled further. These interactions were influenced by conditions predicted by quantum field theories and later explored experimentally in particle accelerators operated by organizations such as CERN, where scientists recreate high-energy collisions that mimic early universe environments to better understand how fundamental particles behave under extreme conditions. Theoretical frameworks such as the Standard Model of Particle Physics describe the properties and interactions of these particles with remarkable accuracy, though they remain incomplete because they do not incorporate gravity at quantum scales. The understanding of particle formation is also rooted in the theoretical insights of physicists like Paul Dirac, who predicted the existence of antimatter and contributed to the development of quantum mechanics that underpins modern particle theory. During this stage, the universe was opaque because photons could not travel freely without scattering off charged particles, meaning that light was trapped within the dense plasma, and no stable atoms could yet form. Nevertheless, the processes occurring during these early moments established the foundation for all subsequent cosmic evolution, including nucleosynthesis and the eventual formation of neutral atoms. Hundreds of thousands of years later, the cooling of the universe gradually reduced the energy of particle collisions, allowing stable combinations to persist for longer periods and enabling the transition from a radiation-dominated era to one in which matter would begin to influence gravitational dynamics more strongly. This shift would ultimately determine how matter clumped together to form larger structures under gravity's influence, and although these events occurred within the first seconds of cosmic history, their consequences extend across billions of years, shaping everything from the composition of stars to the chemistry of planets. The formation of fundamental particles therefore represents a critical bridge between the abstract physics of the early universe and the tangible structures observed today, linking the laws of quantum mechanics with the evolution of galaxies and providing essential insight into how the universe transformed from an energetic plasma into a cosmos capable of supporting complexity, diversity, and eventually life. The study of this epoch continues to advance through both theoretical modeling and experimental investigation, offering deeper understanding of the origins of matter and the processes that determined why the universe exists in its present form rather than dissolving into radiation during its earliest moments. In the earliest measurable fractions of a second after the Big Bang, as the universe continued expanding and cooling from its unimaginably hot and dense beginnings, one of the most profound and mysterious processes in cosmic history unfolded, known as baryogenesis, the mechanism that ultimately determined why matter came to dominate over antimatter in the observable universe. According to fundamental principles of particle physics, every process that creates a particle of matter should also create a corresponding particle of antimatter with identical mass but opposite charge. And in the intense energy conditions of the early universe, such matter and antimatter pairs were constantly being formed and annihilated into pure radiation in a state of dynamic equilibrium. Yet if perfect symmetry had prevailed, then all matter and antimatter would have eventually annihilated each other completely, leaving behind a universe filled only with photons and no atoms, stars, or galaxies. However, observations of the cosmos clearly reveal a universe overwhelmingly composed of matter, with only trace amounts of antimatter found in high-energy processes, implying that during the earliest instance, a slight imbalance emerged in which matter particles outnumbered antimatter particles by roughly 1 in every billion pairs, meaning that for every billion particle-antiparticle pairs that annihilated each other, a single matter particle survived, and these survivors would eventually form all the protons, neutrons, and electrons that make up the visible structures of the universe today. The origin of this asymmetry is not fully understood, but theoretical models suggest that certain conditions known as Sakharov criteria must have been satisfied, including the violation of baryon number conservation, the violation of charge, symmetry and charge parity symmetry, and the occurrence of processes outside of thermal equilibrium. These conditions would allow physical laws to treat matter and antimatter slightly differently under specific interactions, enabling an excess of baryons to remain after annihilation events cease to dominate. Experimental evidence for charge parity violation has been observed in particle decay processes studied in advanced facilities such as Fermi National Accelerator Laboratory, where high-energy collisions allow scientists to investigate how subatomic Particles transform under the influence of fundamental forces. Such experiments have demonstrated that certain interactions involving quarks do not behave identically when matter is replaced by antimatter and spatial coordinates are inverted, providing clues that similar asymmetries may have occurred during the early universe. Theoretical work by physicists including Andrei Sakharov laid the conceptual foundation for understanding how baryogenesis might proceed under the theans. Conditions, though the precise mechanism, remains an active area of research involving extensions to the standard models such as supersymmetry and leptogenesis. During this epoch, the temperature of the universe dropped sufficiently for quarks to become confined within protons and neutrons through the strong nuclear force, while remaining immersed in a sea of photons and neutrinos that influence the rate of particle interactions. The slight excess of baryons that survived annihilation would later participate in nucleosynthesis, forming the first atomic nuclei within minutes of cosmic time, thereby setting the stage for the eventual formation of neutral atoms and the emergence of large-scale structures. Billions of years later, without baryogenesis, the universe would lack the material necessary for stars to ignite and synthesize heavier elements through nuclear fusion processes that ultimately produce the chemical diversity required for planets and biological systems. Thus, this seemingly minute imbalance between matter and antimatter represents one of the most consequential turning points in cosmic evolution, transforming a symmetric particle soup into a matter-dominated universe capable of developing complexity and structure. Ongoing research seeks to identify whether unknown interactions involving neutrinos or hypothetical particles beyond the standard model may account for the observed asymmetry, and future experiments aim to measure charge parity violation with even greater precision to test competing theories. The outcome of these investigations may reveal why the universe contains something rather than nothing, linking the physics of the smallest particles with the grandest scales of cosmic structure, and providing deeper insight into how the laws of nature shape the destiny of the cosmos during its earliest moments. Ultimately, the survival of matter after the annihilation era allowed gravity to amplify tiny density fluctuations, leading to the formation of galaxies, stars, and planets, making baryogenesis a critical process that determined not only the composition of the universe, but also the possibility of life emerging within it. As the universe continued to expand and cool during the first few microseconds following the Big Bang, it passed through an extraordinary phase in which matter existed not in the familiar form of atoms, or even atomic nuclei, but as an exotic state known as quark-gluon plasma, a superheated and extremely dense mixture in which quarks and gluons moved freely, without being confined into composite particles. Under such immense temperatures exceeding trillions of degrees Kelvin, the strong nuclear force that normally binds quarks together inside protons and neutrons became effectively screened, allowing these fundamental constituents to behave as a nearly perfect fluid of interacting particles. During this epoch, the universe was still dominated by radiation, with energy densities so high that collisions between particles occurred constantly, ensuring thermal equilibrium across all available degrees of freedom. Quarks of different types, including up, down, and strange flavors, interacted through gluons, which carried the color charge associated with the strong interaction described by quantum chromodynamics. However, as expansion reduced the average energy per particle, the universe approached a critical transition temperature at which quarks and gluons could no longer remain unbound and began to combine into stable hadrons, such as protons and neutrons, through a process known as hadronization. This transformation marked one of the first major steps toward the formation of matter capable of participating in later nuclear reactions and ultimately chemical processes. The confinement of quarks within hadrons occurred as a strong force became increasingly dominant at lower energies, causing quarks to be trapped inside composite structures whose stability depends on the exchange of gluons within a confined region of space. Modern experimental physics has attempted to recreate conditions similar to this primordial plasma, using particle accelerators such as the Large Hadron Collider where heavy ion collisions briefly generate temperatures and densities comparable to those that existed a few microseconds after the Big Bang. Observations from these experiments suggest that quark-gluon plasma behaves more like an almost frictionless liquid than a gas, revealing unexpected collective properties that challenge earlier theoretical assumptions. During the hadronization phase, baryons formed when three quarks combined, while mesons formed from quark-antiquark pairs, and although most matter-antimatter pairs annihilated due to the asymmetry established earlier, a slight excess of baryons remained, allowing protons and neutrons to persist as stable building blocks for future atomic nuclei. Neutrinos decoupled from matter interactions, shortly afterward carrying away energy and influencing the expansion rate of the universe, while photons continued to interact with charged particles, maintaining a hot plasma environment. The relative abundance of protons and neutrons at the end of this phase would later determine the outcome of primordial nucleosynthesis, in which the first light elements formed. The cooling of the universe also reduced the frequency of particle interactions, enabling matter to transition gradually from a radiation-dominated state to one where mass began to influence gravitational dynamics more strongly. This change allowed tiny fluctuations in density to begin growing under the influence of gravity, eventually leading to the formation of cosmic structures billions of years later. Without the hadronization of quarks into stable particles, the universe would lack the necessary ingredients for nuclear binding and atomic formation, preventing the emergence of stars and galaxies. Therefore, this phase transition from quark-gluon plasma to confined hadronic matter represents a crucial milestone in cosmic evolution, linking the high-energy physics of the early universe to the macroscopic structures observed today. Theoretical models continue to explore how the properties of this plasma may affect the behavior of dark matter candidates or influence phase transitions associated with other fundamental forces, and ongoing experiments aim to refine our understanding of confinement mechanisms and the equation of state governing strongly interacting matter. By studying these processes, scientists hope to gain insight into the physical laws that governed the universe during its first microseconds, and to understand how the interplay between expansion and cooling transformed a seething sea of free quarks into the stable protons and neutrons that would eventually form the nuclei of atoms, paving the way for the development of chemical complexity and the emergence of planets and living systems across cosmic time. Within the first few minutes after the Big Bang, as the universe continued to expand and cool from its previously unimaginable temperatures, conditions finally became suitable for one of the most important processes in cosmic history, known as Big Bang nucleosynthesis. During this epoch, the universe had cooled enough for protons and neutrons formed earlier during the hadronization phase to begin combining through nuclear fusion reactions that produced the first light atomic nuclei. Before this time, the intense thermal energy of the surrounding radiation prevented stable nuclear binding, because high-energy photons were capable of breaking apart any newly formed composite particles almost immediately after their creation. However, as temperatures dropped to about 1 billion degrees Kelvin, deuterium nuclei, composed of one proton and one neutron, could survive long enough to participate in further reactions that led to the formation of helium-4 along with trace amounts of helium-3, lithium-7, and beryllium. The relative abundance of these elements depended critically on the neutron-to-proton ratio, which had been determined earlier by weak interaction processes involving neutrinos that interconverted neutrons and protons until these interactions froze out as the universe cooled. At the onset of nucleosynthesis, roughly 1 neutron existed for every 6 protons, and because neutrons are slightly heavier and unstable outside nuclei, some decayed before being incorporated into helium nuclei, resulting in about 25% of the baryonic matter in the universe becoming helium, while the remainder remained as hydrogen. These primordial abundances have been confirmed through astronomical observations of ancient gas clouds and stars, providing one of the strongest pieces of evidence supporting the Big Bang model of cosmology. The precise calculations of element formation during this period also depend on the expansion rate of the universe, which in turn is influenced by the density of matter and radiation, including contributions from neutrinos and any hypothetical additional relativistic particles. Modern measurements of the cosmic microwave background radiation, obtained by missions such as the Planck Space Observatory, have helped refine our understanding of these parameters, allowing theoretical predictions of light element abundances to match observations with remarkable accuracy. The synthesis of helium and other light nuclei effectively ended after about 20 minutes when temperatures fell too low for nuclear fusion to continue efficiently, leaving behind a universe composed primarily of hydrogen and helium gas that would later serve as the raw material for star formation. Heavier elements such as carbon, oxygen, and iron would not be produced until much later inside the cores of stars through stellar nucleosynthesis processes. The successful formation of these first nuclei marked the transition from a universe dominated by elementary particles to one capable of developing chemical structure, because once electrons eventually combined with these nuclei, hundreds of thousands of years later, neutral atoms could form, enabling the decoupling of matter and radiation. Big Bang nucleosynthesis also provides a sensitive probe of physics beyond the standard model, because any deviation in fundamental constants or additional particle species present during this epoch would alter predicted abundances in measurable ways. Observations of lithium in particular have revealed a discrepancy between theoretical predictions and measured values in old stars, leading to ongoing investigations into possible explanations, including nuclear reaction, uncertainties, or new particle interactions. Nevertheless, the overall agreement between theory and observation for hydrogen and helium remains a cornerstone of modern cosmology. This early nuclear chemistry set the stage for all future astrophysical evolution, because without an initial supply of helium, stellar ignition would occur differently, and the pathways for producing heavier elements essential for planets and life would be fundamentally altered. Thus, Big Bang nucleosynthesis represents not only the birth of the first atomic nuclei, but also the foundation upon which the entire chemical diversity of the universe would later be built, linking the physics of the first minutes after the Big Bang to the formation of galaxies, stars, and ultimately the biological systems that emerge billions of years afterward. One of the most profound mysteries in the history of the universe emerged during the earliest fractions of a second after the Big Bang, when matter and antimatter were created in nearly equal quantities through high-energy particle interactions, converted radiation into particle-antiparticle pairs. According to the known laws of physics, every particle of matter, such as electrons, quarks, and protons, should have been accompanied by an antimatter counterpart possessing identical mass but opposite electric charge and quantum numbers, and when matter meets antimatter, they annihilate each other completely, converting their mass back into pure energy in the form of photons. If the universe had remained perfectly symmetric in this respect, then all matter and antimatter would have mutually destroyed each other within the first moments after creation, leaving behind a cosmos filled only with radiation and no atoms, stars, or galaxies. However, the observable universe today is clearly dominated by matter, indicating that some mechanism must have slightly favored matter over antimatter during these primordial interactions, resulting in a tiny excess of matter estimated to be roughly 1 extra particle of matter for every billion particle-antiparticle pairs. After the majority of matter and antimatter annihilated each other, this small surplus remained, forming the building blocks of all cosmic structures that would later develop. This imbalance is known as baryon asymmetry, and its origin remains one of the central unsolved problems in cosmology and particle physics. Theoretical physicist Andrei Sakharov proposed 3 essential conditions that must be satisfied for such an asymmetry to arise, including baryon number violation, charge parity, symmetry violation, and interactions occurring outside thermal equilibrium. Experimental evidence for CP violation has been observed in certain weak nuclear interactions involving subatomic particles known as mesons, providing partial support for the idea that matter and antimatter behave slightly differently under specific circumstances. large particle accelerators, such as those operated by the CERN, continue to investigate these phenomena by recreating high-energy conditions, similar to those present shortly after the Big Bang, in order to measure tiny differences between matter and antimatter decay processes. Various theoretical models attempt to explain how baryogenesis might have occurred, including electroweak baryogenesis and leptogenesis, which suggests that asymmetries in the behavior of leptons, such as neutrinos, could have indirectly produced the observed excess of baryonic matter through complex interactions in the early universe. The consequences of this slight imbalance are immense, because without it the hydrogen and helium formed during Big Bang nucleosynthesis would never have existed, and gravitational attraction would have had no material substance to act upon preventing the formation of galaxies, stars, and planetary systems. The survival of matter also allowed for the later emergence of chemical complexity, leading to molecules, organic compounds, and ultimately biological life. Ongoing experiments studying neutrino oscillations and proton decay aim to test extensions of the standard model of particle physics that might account for baryon number violation, while astrophysical observations of the cosmic microwave background provide constraints on the overall matter density, consistent with the predicted matter excess. Some speculative theories even propose that antimatter-dominated regions of the universe could exist beyond our observable horizon, though no definitive evidence for such domains has yet been found. The asymmetry between matter and antimatter thus represents a subtle but crucial feature of the universe's origin, because it transformed what could have been a featureless sea of radiation into a structured cosmos filled with galaxies and stars. The existence of every atom within planets, living organisms, and interstellar gas ultimately depends on this minute imbalance that occurred during the universe's earliest moments, demonstrating how small deviations in fundamental physical processes can lead to enormous consequences over cosmic timescales, shaping the very possibility of existence itself. Within the first few minutes after the Big Bang, the universe had cooled enough from its initial extremely hot and dense state to allow the formation of the very first atomic nuclei in a process known as Big Bang nucleosynthesis, which represents one of the earliest and most critical stages in cosmic evolution, because it established the initial chemical composition of the universe that would later influence the development of stars, galaxies, and planets. Before this epoch, temperatures were so high that protons and neutrons could not remain bound together, as nuclear forces were constantly disrupted by energetic photons. But as expansion continued, the average temperature dropped to about 1 billion degrees Kelvin, enabling nuclear fusion reactions to occur between free protons and neutrons that had been produced earlier during particle formation processes. So the balance between neutron decay and nuclear binding became essential, since free neutrons are unstable and decay into protons with a half-life of about 10 minutes, meaning that only those neutrons captured quickly enough in fusion reactions would survive to form heavier nuclei. The first step in this process involved the creation of deuterium nuclei composed of one proton and one neutron. However, even deuterium formation required temperatures to fall below a certain threshold, because otherwise high-energy photons would immediately break apart any newly formed nuclei in what is known as the deuterium bottleneck. Once the universe cooled sufficiently to overcome this barrier, a cascade of fusion reactions rapidly converted deuterium into helium-3, helium-4, and small traces of lithium and beryllium, resulting in a primordial mixture consisting of approximately 75% hydrogen and 25% helium by mass, along with minute amounts of other light elements. This predicted abundance has been confirmed through observations of ancient gas clouds and the analysis of cosmic microwave background data collected by missions such as the Wilkinson Microwave Anisotropy Probe, which provided precise measurements of baryon density consistent with theoretical models of nucleosynthesis. The relative proportions of hydrogen and helium formed during this period were determined by the neutron-to-proton ratio, which itself depended on weak nuclear interactions that had frozen out slightly earlier, when the universe was about 1 second old. making Big Bang nucleosynthesis a powerful test of fundamental physics because any deviation in interaction rates or particle properties would alter the predicted elemental abundances observed today. Unlike stellar nucleosynthesis, which occurs over millions or billions of years inside stars, Big Bang nucleosynthesis was completed within roughly 20 minutes after the initial expansion, after which temperatures became too low for further fusion reactions to take place, leaving the universe filled with ionized plasma, consisting of free electrons, nuclei, and photons. This primordial composition played a crucial role in later cosmic history because hydrogen served as the primary fuel for the first generation of stars, while helium contributed to their internal pressure and energy production processes, enabling gravitational collapse and nuclear ignition to occur. The scarcity of heavier elements meant that early star formation involved massive short-lived stars that would later enrich the interstellar medium through supernova explosions, seeding future generations of stars with carbon, oxygen, and other heavier elements necessary for planet formation and life. Modern cosmological observations continue to refine measurements of primordial deuterium and helium in distant low metallicity regions, providing increasingly accurate tests of nucleosynthesis predictions and offering insights into the number of neutrino species and other parameters of the early universe. Any discrepancy between predicted and observed abundances could signal new physics beyond the standard model, including exotic particles or additional interactions that influenced expansion rates during nucleosynthesis. Thus, Big Bang nucleosynthesis stands as one of the earliest observable imprints of the universe's infancy, linking fundamental particle interactions with large-scale cosmic structure and demonstrating how the formation of the simplest atomic nuclei during the first minutes after the Big Bang laid the chemical foundation for everything that would later emerge, including stars, galaxies, planets, and eventually biological organisms capable of studying their own cosmic origins. Approximately 380,000 years after the Big Bang, the universe entered a pivotal phase known as the recombination era, a period during which the universe cooled sufficiently for free protons and electrons to combine and form neutral hydrogen and helium atoms, a process that fundamentally altered the behavior of matter and radiation and set the stage for the emergence of large-scale cosmic structures such as galaxies and clusters. Before recombination, the universe existed as a hot, dense plasma, in which free electrons scattered photons continuously, rendering the universe opaque, and preventing light from traveling freely. This state is analogous to a fog in which photons constantly bounced off charged particles, unable to escape. But as expansion cooled the universe to around 3,000 degrees Kelvin, the kinetic energy of electrons decreased to a point where electromagnetic attraction between negatively charged electrons and positively charged nuclei overcame thermal motion, allowing stable neutral atoms to form. This transition dramatically reduced the scattering of photons and enabled them to move unhindered through space, a phenomenon referred to as photon decoupling. The photons released at this moment now constitute the cosmic microwave background, CMB, radiation, a faint afterglow that permeates all of space and provides an invaluable snapshot of the universe at the time of recombination. Observations of the CMB by missions such as the COBE, WMP, and Planck Space Observatory have revealed tiny fluctuations in temperature corresponding to variations in matter density, which would later evolve under gravity into galaxies and larger structures. The formation of neutral atoms also marked the end of the radiation-dominated era and the beginning of the matter-dominated era, as photons now traveled freely, while the gravitational influence of matter began to dominate the dynamics of cosmic evolution. This transition is critical because it allowed density perturbations, seeded earlier by quantum fluctuations during inflation, to grow through gravitational instability, ultimately leading to the first stars and galaxies. Recombination also influenced the chemical composition of the universe, leaving behind primarily hydrogen and helium with trace amounts of lithium, which would serve as the raw materials for future star formation. The physics of recombination involves detailed interactions between photons, electrons, and nuclei, including processes such as Lyman alpha transitions and two-photon decay, which determine the timing and efficiency of atom formation. Precise modeling of these processes is essential for interpreting CMB observations and for understanding the subsequent formation of the first cosmic structures. In addition, recombination had a direct impact on the temperature and polarization anisotropies observed in the CMB, providing key insights into fundamental cosmological parameters such as the total matter density, dark matter density, and the expansion rate of the universe. The era of recombination thus represents a profound turning point in cosmic history, transforming a uniform, opaque plasma into a transparent cosmos where light could travel freely and gravitational forces could shape matter into the first galaxies, clusters, and superclusters. This process illustrates how fundamental interactions at the atomic level directly influence the large-scale architecture of the universe. Without recombination, photons would have remained trapped, the CMB would not exist, and the growth of cosmic structures would have been delayed, fundamentally altering the evolution of the cosmos. Moreover, recombination set the stage for the later formation of molecular hydrogen, which played a crucial role in cooling gas clouds and enabling the collapse of the first stars. Understanding recombination is also critical for interpreting observations of distant quasars and galaxies, as the ionization history of the universe leaves an imprint on the intergalactic medium that can be traced through absorption lines and other observational signatures. Overall, the recombination era exemplifies the profound connection between microphysical processes and cosmic evolution, demonstrating how the formation of neutral atoms allowed light to escape, matter to clump, and the universe to transition from a homogeneous plasma to a structured cosmos capable of supporting the complex hierarchy of galaxies, stars, planets, and ultimately life itself. Following the recombination era, when neutral atoms first formed and the universe became transparent to radiation, the photons released at that moment began traveling freely through space, creating a relic radiation field now known as the cosmic microwave background, CMB, a phenomenon that provides the most direct observational evidence of the universe's infancy and allows scientists to study conditions nearly 380,000 years after the Big Bang with extraordinary precision. The CMB consists of a nearly uniform sea of photons exhibiting a blackbody spectrum, corresponding to a temperature of approximately 2.7 Kelvin today, slightly cooled due to the ongoing expansion of the universe over billions of years. Despite its remarkable uniformity, precise measurements by missions such as COBE, WMAP, and Planck Space Observatory have revealed tiny anisotropies minute variations in temperature on the order of 1 part in 100,000 that reflect primordial density fluctuations seeded during the inflationary epoch. These fluctuations provided the gravitational wells necessary for matter to accumulate and eventually form stars, galaxies, and clusters, making the CMB a crucial probe of the initial conditions of cosmic structure formation. The polarization of the CMB also carries valuable information about the early universe, including the imprint of Thomson scattering between photons and free electrons and the potential signature of primordial gravitational waves generated during inflation, which if detected could provide direct evidence for this rapid expansion phase and offer insights into the physics of the universe at energy scales far beyond the reach of terrestrial experiments. Detailed analysis of the CMB allows cosmologists to infer key parameters of a universe, including the total density of matter and energy, the relative contributions of dark matter and dark energy, the Hubble constant, and the curvature of spacetime, confirming that the universe is flat on large scales, and that dark energy dominates its energy budget today. Moreover, the CMB serves as a reference frame for the observable universe, providing a cosmic backdrop against which motions of galaxies and large-scale structures can be measured. Tiny anisotropies in the CMB also reveal information about the baryon-to-photon ratio, which constrains theories of Big Bang nucleosynthesis and the abundance of light elements such as hydrogen, helium, and lithium. The discovery of the CMB in 1965 by Arno Penzias and Robert Wilson provided pivotal evidence for the Big Bang model, confirming that the universe had a hot, dense origin rather than a static or steady-state configuration. Subsequent mapping of the CMB has enabled scientists to develop sophisticated cosmological models that describe the evolution of the universe from its earliest moments through the formation of the first galaxies and up to its present accelerated expansion, influenced by dark energy. Beyond its scientific importance, the CMB represents a profound testament to the universe's history, offering a window into conditions when the cosmos was only a fraction of a million years old, a time when atoms were forming, photons were decoupling, and the seeds of cosmic structure were established. Its uniformity underscores the success of the inflationary theory in explaining the large-scale homogeneity and isotropy of the cosmos, while the slight anisotropies provide critical clues about the mechanisms that drove structure formation. Analysis of the CMB also informs our understanding of the matter-antimatter, asymmetry, neutrino physics, and potential new physics beyond the standard model, as deviations from expected patterns could indicate unknown processes or particles influencing early cosmological evolution. In essence, the cosmic microwave background is both a relic of the universe's birth and a detailed map of its infancy, allowing scientists to reconstruct events that occurred billions of years ago, and to understand the physical processes that shaped the universe from a nearly uniform plasma into a richly structured cosmos filled with galaxies, stars, planets, and ultimately, life. Its study continues to drive advancements in observational cosmology, particle physics, and theoretical models, ensuring that the CMB remains one of the most important and enduring tools for exploring the origins and evolution of the universe. Following recombination and the decoupling of photons that produce the cosmic microwave background, the universe entered a long period known as the Dark Ages, an epoch lasting from approximately 380,000 years to several hundred million years after the Big Bang, during which the cosmos was filled with neutral hydrogen and helium gas, but devoid of luminous sources such as stars or galaxies, making it an era of darkness in the literal sense. During this period, the universe continued to expand and cool, and matter began to respond more strongly to gravitational forces as radiation pressure decreased, allowing small density fluctuations, seeded during inflation and preserved in the cosmic microwave background, to grow. These slight overdensities in the otherwise homogeneous gas began to accumulate matter, slowly forming the first dark matter halos that would later serve as the gravitational scaffolding for galaxy formation. Despite the growth of structure at these scales, there were no significant sources of light, because the gas had not yet collapsed into dense enough regions to ignite nuclear fusion, resulting in a universe largely opaque to visible observation, but not entirely invisible to other forms of radiation. The neutral hydrogen during the Dark Ages played a key role in absorbing high-energy photons, producing spectral features that can still be traced through the 21-centimeter hydrogen line, offering cosmologists a unique tool to study the distribution of matter during this otherwise inaccessible period. During the Dark Ages, the temperature of baryonic matter dropped as the universe expanded, and the first gravitationally bound structures began to form through hierarchical clustering, with smaller halos merging into larger structures under the influence of dark matter and gravity. This process laid the groundwork for the eventual formation of the first stars and galaxies, as the densest regions could eventually cool via molecular hydrogen formation, allowing gas to collapse further. The physics of this epoch involves complex interactions between gravity, hydrodynamics, thermodynamics, and radiation transport, and it sets the stage for the end of the Dark Ages with the onset of the first luminous objects, a process referred to as cosmic dawn. Observationally, the Dark Ages are challenging to study directly because There were no stars or galaxies emitting visible light, but indirect evidence comes from measurements of the cosmic microwave background, large-scale structure, and absorption features in the spectra of distant quasars that trace neutral hydrogen distribution. The Dark Ages also represent a critical testing ground for theories of dark matter, as the formation of the earliest structures depends sensitively on its properties, distribution, and interaction with baryonic matter. Numerical simulations and theoretical models of this epoch aim to reproduce the initial conditions and evolution of matter over hundreds of millions of years, providing predictions that can be tested against observations of high redshift galaxies, quasars, and the 21-centimeter signal. The transition from the Dark Ages to the era of reionization, when the first stars and galaxies ignited, dramatically altered the universe by introducing ultraviolet radiation that ionized neutral hydrogen, ending this period of darkness and beginning the cosmic epoch dominated by luminous sources. Understanding the Dark Ages is crucial for comprehending the sequence of events that led to galaxy formation, star formation, and ultimately the cosmic structures observed today. By studying the processes that governed this era, scientists can gain insight into the behavior of matter under primordial conditions, the role of dark matter in shaping structure, and the physical mechanisms that led to the ignition of the first stars. The Dark Ages thus represent both a literal and figurative period of cosmic uncertainty, a time when the universe was dark but evolving silently, setting the stage for the brilliant structures and complex phenomena that would emerge in the subsequent epochs, highlighting the deep connection between fundamental physics, gravity, and cosmic evolution in the early universe. Following the Dark Ages, the universe entered a transformative epoch known as cosmic dawn, approximately 100 to 400 million years after the Big Bang, characterized by the formation of the first stars, also called population 3 stars, which illuminated the cosmos for the first time and initiated profound changes in the physical, chemical, and radiative state of the universe. Prior to this epoch, the universe consisted largely of neutral hydrogen and helium gas, with small density fluctuations seeded during inflation, gradually growing under gravity, into the earliest dark matter halos. Within these halos, baryonic matter cooled through processes such as molecular hydrogen formation, allowing gas clouds to collapse under their own gravity to form dense regions capable of igniting nuclear fusion. The first stars were likely massive, tens to hundreds of times the mass of the Sun, and their formation marked the transition from a dark, structureless universe to one populated with luminous objects, bringing an end to the so-called cosmic Dark Ages. These stars emitted intense ultraviolet radiation, ionizing the surrounding hydrogen gas and creating pockets of ionized regions that would eventually merge during the reionization epoch, fundamentally altering the transparency and thermal state of the intergalactic medium. The birth of the first stars also initiated the first processes of chemical enrichment, as supernova explosions from massive population 3 stars dispersed heavier elements into the surrounding gas, providing the raw material for subsequent generations of stars and eventually planets and life. Observations of high redshift galaxies and quasars, along with indirect evidence from the cosmic microwave background and 21-2 centimeter line studies, provide critical insights into the timing and properties of cosmic dawn, although many details remain uncertain due to the extreme distances and faintness of these early objects. Theoretical models and numerical simulations help predict the mass, luminosity, and distribution of the first stars, suggesting that their formation was heavily influenced by the distribution of dark matter, cooling efficiency of primordial gas, and feedback mechanisms from radiation and supernovae. Feedback from the first stars had a profound impact on subsequent structure formation, as radiation pressure and supernova-driven winds regulated star formation in neighboring halos, influenced the temperature and ionization state of the surrounding gas, and contributed to the large-scale reionization of the universe. The cosmic dawn also set the stage for the formation of the first galaxies, as stars formed within dark matter halos merged and clustered under gravity, eventually producing the hierarchical structures observed in the modern universe. Studying this epoch allows cosmologists to test models of early star formation, dark matter properties, and the interplay between radiation and gas in shaping the first luminous structures, providing critical constraints for understanding the evolution of galaxies and cosmic large-scale structure. The onset of cosmic dawn also influences the interpretation of observations of the cosmic microwave background, as energy injected by the first stars affects the ionization history and leaves subtle imprints on CMB polarization patterns. Moreover, the formation of the first stars represents the beginning of stellar nucleosynthesis for heavier elements, a process that would eventually generate carbon, oxygen, and other elements necessary for planets and life. In essence, cosmic dawn represents a critical turning point in the universe's history, transforming it from a dark and diffuse medium into one where energy, light, and complexity began to emerge. This epoch illustrates how gravitational physics, chemistry, radiation processes, and feedback mechanisms interacted to produce the first stars, laying the foundation for galaxies, planets, and the eventual emergence of life. Understanding cosmic dawn not only illuminates the processes that led to the universe's first sources of light, but also provides a context for studying the evolution of galaxies, chemical enrichment, and the cosmic history of star formation, highlighting the intricate connections between the microphysical processes of gas cooling nuclear fusion and the radiation and the grand structure of the universe observed billions of years later. Following cosmic dawn, the universe entered the epoch of reionization, a transformative period that occurred roughly between 400 million and 1 billion years after the Big Bang, during which the ultraviolet radiation from the first stars, galaxies, and quasars reionized the neutral hydrogen that had dominated the intergalactic medium since recombination. Prior to this epoch, the universe had become largely transparent following recombination, but most of the hydrogen remained neutral, rendering large-scale structures difficult to observe in optical wavelengths, and maintaining a state in which light could travel freely only through non-ionizing paths. The intense ultraviolet radiation emitted by the earliest luminous objects initiated the process of ionizing hydrogen atoms by stripping electrons from protons, gradually creating expanding bubbles of ionized gas that grew and eventually overlapped, converting the majority of the intergalactic medium into a highly ionized state. This reionization profoundly altered the thermal and chemical properties of the universe, influencing the formation of subsequent generations of galaxies and regulating the growth of structure by changing the cooling efficiency of gas and affecting the pressure of the intergalactic medium. Observational evidence of reionization comes from multiple sources, including the analysis of quasar spectra, showing Gunn-Pedersen troughs, measurements of the polarization of the cosmic microwave background, one people in the polarization of the cosmic microwave background, and studies of the 21-centimeter hydrogen line, all of which provide insights into the timing, duration, and topology of the process. Reionization is believed to have been driven primarily by the combined output of massive population 3 stars, early galaxies, and accreting supermassive black holes in quasars, with the relative contributions of these sources still a subject of active research. Numerical simulations of reionization incorporate complex physics, including radiative transfer, star formation, feedback mechanisms, and the clustering of dark matter halos, allowing cosmologists to predict the size distribution of ionized bubbles, the evolution of the ionization fraction, and the impact on observable signals at high redshift. The completion of reionization marked a pivotal moment in cosmic history, establishing the large-scale ionized universe observed today, and setting the stage for the subsequent formation and evolution of galaxies over billions of years. The thermal feedback from reionization increased the gene's mass, suppressing star formation in low-mass halos while allowing more massive structures to grow, thus influencing the hierarchical development of galaxies. The process of reionization also left subtle imprints on the cosmic microwave background, in the form of polarization anisotropies, which provide independent constraints on the timing and duration of this epoch. Furthermore, understanding reionization I is critical for interpreting observations of high redshift galaxies, and the intergalactic medium, as the ionization state, affects the transmission of light and the detectability of early structures. The chemical enrichment initiated by the first stars during reionization also contributed to the formation of heavier elements beyond hydrogen and helium, seeding the universe with the building blocks necessary for planets and life. In essence, the epoch of reionization represents the final major phase transition of the early universe, transforming it from a neutral dark state into a luminous, ionized cosmos capable of supporting complex structure formation. It exemplifies the interplay between radiation, matter, and gravity on cosmic scales, highlighting how the first sources of light influence the evolution of the intergalactic medium, the formation of galaxies, and the observable properties of the universe, billions of years later. By studying reionization, scientists can probe the nature of the first stars, the growth of early galaxies, the behavior of intergalactic gas, and the emergence of large-scale structure, making this epoch an essential component in understanding the full narrative of cosmic evolution, from the Big Bang to the universe we observe today. As the universe emerged from the epoch of reionization, the small-scale density fluctuations present in the primordial matter distribution continued to grow under the influence of gravity, leading to the formation of the first galaxies, the initial cosmic islands of stars, gas, and dark matter that would serve as the foundational building blocks of the large-scale structure observed in the modern universe. These first galaxies formed within dark matter halos, which provided the gravitational potential wells necessary to capture and retain baryonic matter, allowing gas to cool, condense, and eventually ignite nuclear fusion to form stars. The hierarchical model of galaxy formation suggests that small halos merged over time to produce larger systems, establishing the framework for the complex web of galaxy clusters, filaments, and voids observed today. The earliest galaxies were likely small, irregular, and dominated by massive, short-lived population 3 stars that produced intense ultraviolet radiation, contributing to the ongoing reionization of the intergalactic medium. The chemical composition of these galaxies was initially pristine, consisting primarily of hydrogen and helium, but supernova explosions from the first generations of stars enriched the interstellar medium with heavier elements, or metals, enabling subsequent generations of stars to form with increasingly complex chemistry. Observations of high redshift galaxies using powerful telescopes, such as the Hubble Space Telescopes and the James Webb Space Telescope and the James Webb Space Telescope, have begun to reveal the properties of these early galaxies, including their masses, star formation rates, luminosities, and spectral characteristics, providing empirical constraints on models of galaxy formation. Theoretical simulations, incorporating dark matter dynamics, gas cooling, star formation, feedback from supernovae, and radiative transfer are critical for understanding how these first galaxies evolved, how they interacted with their surroundings, and how they contributed to the ionization and chemical enrichment of the universe. Feedback processes played a crucial role in regulating star formation within early galaxies, as energy and momentum from supernovae and stellar winds could expel gas from shallow potential wells, temporarily suppressing further star formation, while also spreading heavy elements into the surrounding medium. The first galaxies also served as the seeds for supermassive black holes, which would grow through accretion and mergers to power the earliest quasars, further influencing their environments through energetic radiation and jets. Studying the formation and evolution of the first galaxies provides critical insights into the initial conditions that shaped the cosmic web, the mass function of dark matter halos, and the efficiency of star formation in low metallicity environments. These galaxies also serve as laboratories for testing models of feedback, chemical enrichment, and the role of dark matter in structure formation. Understanding the earliest stages of galaxy formation informs our knowledge of the subsequent evolution of galaxy morphology the assembly of galactic disks and bulges, and the emergence of spiral and elliptical galaxies in later epochs. Furthermore, the distribution and properties of the first galaxies are intimately connected to the reionization history of the universe, as their ionizing radiation created the bubbles of ionized hydrogen that eventually percolated to complete cosmic reionization. The study of these primordial galaxies therefore links the physics of star formation, nucleosynthesis, radiative processes, and dark matter to the grand architecture of the cosmos, illustrating how small initial fluctuations evolved into the complex network of galaxies, clusters, and filaments that define the large-scale structure of the universe. By examining the first galaxies, scientists can trace the evolution of cosmic chemistry, the growth of structure, and the interplay between radiation and matter that governed the early universe, shedding light on the origins of the stars, planets, and ultimately life that would emerge billions of years later. These early cosmic islands set the stage for the hierarchical growth of structure, the formation of galaxy clusters, and the eventual development of the vast interconnected cosmic web, making the study of first galaxies essential for understanding the full narrative of cosmic evolution from the Big Bang to the universe as we observe it today. As the universe progressed beyond the formation of the first galaxies, gravity continued to amplify initial density fluctuations imprinted during inflation, giving rise to the large-scale structure known today as the cosmic web, an intricate network of filaments, sheets, clusters, and voids spanning hundreds of millions of light-years and connecting galaxies across vast cosmic distances. These structures emerged as dark matter, which constitutes the majority of the universe's matter content, gravitationally collapsed into halos and filaments, providing the scaffolding upon which baryonic matter, gas, stars, and galaxies could accumulate, evolve, and form more massive cosmic structures. The interplay between dark matter dynamics and baryonic physics, including gas cooling star formation and feedback from supernovae and active galactic nuclei, shaped the distribution, morphology, and evolution of galaxies within these large-scale structures. Numerical simulations, such as the Millennium and Illustris projects, have been instrumental in modeling the formation and evolution of the cosmic web, reproducing the observed distribution of galaxies and matter while providing insights into the role of dark matter in structure formation. Observational evidence from galaxy surveys, including the Sloan Digital Sky Survey, SDSS, and the Dark Energy Survey, DSS, has revealed the filamentary nature of matter distribution with dense galaxy clusters located at the nodes of the network, and vast underdense voids occupying the spaces between filaments, confirming theoretical predictions. The growth of large-scale structure is also influenced by the expansion rate of the universe and the properties of dark energy, which governs the acceleration of cosmic expansion and affects the rate at which matter can collapse under gravity. The formation of clusters and superclusters represents the hierarchical nature of structure growth, with smaller galaxies and groups merging over time to create more massive systems, while feedback processes regulate star formation and chemical enrichment within these structures. Large-scale structures serve as laboratories for studying galaxy evolution, environmental effects, and interactions between galaxies, as dense regions promote mergers, tidal interactions, and accelerated star formation, while voids provide environments where isolated galaxies evolve more slowly. The cosmic web also impacts the propagation of light from distant sources, producing gravitational lensing effects that can be used to map the distribution of dark matter and test cosmological models. Understanding the formation and evolution of the cosmic web provides key insights into the distribution of baryonic and dark matter, the influence of dark energy on structure growth, and the mechanisms driving galaxy formation and evolution across cosmic time. The interconnected nature of the cosmic web highlights the influence of initial conditions in the early universe, demonstrating how tiny quantum fluctuations amplified by inflation evolved into the vast network of structures observed today. Moreover, the distribution and dynamics of large-scale structures inform studies of cosmological parameters, such as the matter density parameter, the amplitude of matter fluctuations, C8, and the who blank by no constant, linking observational data with theoretical models of the universe's evolution. By examining filaments, clusters, and voids, astronomers can reconstruct formation, study the assembly of galaxies within different environments, and investigate the role of feedback processes in shaping galaxy properties. The cosmic web thus represents the culmination of billions of years of gravitational evolution, connecting microphysical processes in the early universe to macroscopic structures spanning hundreds of millions of light-years, illustrating the intricate interplay between matter, energy, and gravity. In essence, the emergence of large-scale structure transformed the universe from a nearly uniform distribution of matter into a highly organized, hierarchical network, establishing the framework within which galaxies, stars, planets, and ultimately life would develop, and providing a direct link between the physics of the early universe and the observable cosmos, enabling scientists to study the underlying principles that govern cosmic evolution and structure formation on the grandest scales. As cosmic structures continued to grow through the hierarchical merging of dark matter halos and galaxies, some regions of the universe developed into the largest gravitationally bound systems known as galaxy clusters, enormous conglomerations containing hundreds to thousands of galaxies, vast amounts of hot intracluster gas, and enormous reservoirs of dark matter that collectively define some of the most massive objects in the cosmos. These clusters formed at the nodes of the cosmic web, where filaments intersected, providing the densest environments in the large-scale structure, and their formation is governed by the interplay of gravity, baryonic physics, and feedback processes over billions of years. The growth of galaxy clusters begins with the accumulation of smaller galaxy groups and individual galaxies, which are drawn together by their mutual gravitational attraction, merging over time to form larger and more massive clusters. The intracluster medium, composed primarily of highly ionized hydrogen and helium heated to tens of millions of degrees Kelvin, emits copious X-ray radiation, allowing astronomers to observe clusters and study their mass distribution, temperature, and chemical composition through X-ray telescopes such as Chandra X-ray Observatory and XMN Newton. Dark matter dominates the total mass of galaxy clusters, typically constituting about 80 to 85% of the mass, while baryonic matter, including galaxies and hot gas, makes up the remainder. Gravitational lensing of background light by the cluster's mass provides an independent method to map the dark matter distribution and study its properties. Clusters also contain complex dynamical processes, including galaxy interactions, mergers, and ram pressure stripping, where galaxies moving through the dense intracluster medium lose gas and experience altered star formation rates. These processes influence the evolution of cluster galaxies, leading to the prevalence of elliptical galaxies and the quenching of star formation in dense cluster environments, compared to more isolated regions. The formation of galaxy clusters is influenced by the large-scale matter distribution, with regions of higher density experiencing accelerated growth due to enhanced gravitational attraction and cosmological parameters, including the dark energy density and matter density, affecting the rate at which clusters assemble. Observations of cluster abundance, distribution, and mass provide crucial constraints on cosmological models, allowing scientists to test theories of structure formation, the properties of dark matter, and the evolution of the universe's X-produce engine. The presence of supermassive black holes in cluster galaxies, particularly in central dominant galaxies, contributes to feedback processes that regulate the heating and cooling of intracluster gas, influencing star formation and chemical enrichment over time. Clusters also host a population of globular clusters, dwarf galaxies, and intracluster stars, providing a detailed record of the formation history and interactions of member galaxies. The chemical composition of intracluster gas, enriched by supernova explosions from cluster galaxies, reveals information about the nucleosynthesis history and the cumulative star formation within the cluster environment. Studying galaxy clusters also enables the observation of large-scale phenomena such as cluster mergers, shocks, and radio halos, which provide insights into plasma physics and the behavior of dark matter during collisions. Clusters act as cosmic laboratories for testing fundamental physics, including general relativity, particle interactions, and the properties of dark energy, as their abundance and evolution over cosmic time are sensitive to these underlying principles. The discovery and study of clusters. For nearby systems like the Coma cluster to distant high redshift clusters, allow astronomers to trace the growth of structure across billions of years, providing a direct link between the early universe density fluctuations and the massive structures observed today. Galaxy clusters thus serve as both endpoints of hierarchical structure formation and essential tools for understanding the dynamics, composition, and evolution of the cosmos, connecting the microphysical processes of baryons and dark matter to the large-scale architecture of the universe. In essence, the formation of galaxy clusters represents the assembly of cosmic giants, highlighting the interplay between gravity, dark matter, baryonic physics, and cosmic time, illustrating how the universe evolved from initial density fluctuations into a richly structured cosmos capable of supporting galaxies, stars, planets, and ultimately life, and providing a cornerstone for observational cosmology and our understanding of the universe's history. As the universe matured beyond the formation of galaxies and clusters, the large-scale distribution of matter coalesced into an intricate network known as the cosmic web, composed of filaments, sheets, and vast voids, which collectively form the structural skeleton of the cosmos. Filaments are elongated structures composed of dark matter, galaxies, and intergalactic gas, stretching across hundreds of millions of light-years, connecting massive galaxy clusters at their nodes, and guiding the flow of matter through gravitational attraction. In contrast, voids are enormous under dense regions with relatively few galaxies and low matter density, often spanning tens to hundreds of millions of light-years, representing the spaces between the filaments. This organization emerged from the amplification of primordial density fluctuations, imprinted during inflation, with gravitational instability driving matter to accumulate in dense regions and evacuate low-density areas, producing the interconnected network observed today. Observational evidence of filaments and voids comes from large galaxy redshift surveys, such as the Sloan Digital Sky Survey, SDSS, and a 2DEF Galaxy Redshift Survey, which map the three-dimensional positions of millions of galaxies, revealing the striking web-like arrangement. The dark matter within filaments provides the dominant gravitational potential, drawing baryonic matter along the filaments and promoting galaxy formation in these dense environments. Filaments serve as conduits for matter and gas, channeling material into galaxy clusters and influencing the growth and evolution of structures within the cosmic web. The physical properties of filaments include varying galaxy densities, gas temperatures, and magnetic field strengths, with intergalactic gas within filaments, often forming warm-hot intergalactic medium, WIM, at temperatures of 10 circumflex 5 to 10 circumflex 7 Kelvin, detectable through X-ray and ultraviolet absorption studies. Voids, while relatively empty, play a critical role in cosmology, providing low-density environments where galaxies evolve in isolation, offering insights into galaxy formation processes absent strong environmental effects. The dynamics of filaments and voids influence cosmic flows, shaping the peculiar velocities of galaxies and impacting the large-scale motion of matter. Simulations of cosmic structure formation, including N-body and hydrodynamic models, reproduce the filamentary and void structures with remarkable fidelity, allowing comparison with observations to test cosmological parameters, dark matter properties, and the influence of dark energy on structure growth. Filaments also host a variety of galaxy types, from massive spirals to small dwarf galaxies, and their interactions within these elongated structures can trigger star formation, mergers, and other evolutionary processes. Magnetic fields and shock waves within filaments, affect the dynamics of intergalactic gas and the thermal history of baryonic matter, influencing the efficiency of star formation in galaxies embedded within these structures. Cosmic voids provide a complementary laboratory for testing cosmological theories, as their low-density nature makes them sensitive to dark energy, modifications of gravity, and the distribution of dark matter, with void shapes, sizes, and expansion rates serving as probes of underlying physics. Observations of the Lyman alpha forest, which traces neutral hydrogen along lines of S, white to distant quasars, offer a means to study the matter distribution within filaments and voids, providing insights into the thermal and chemical evolution of the intergalactic medium. The cosmic web's filamentary and void structures highlight the hierarchical nature of structure formation, connecting the initial tiny density perturbations from the early universe to the vast, organized distribution of matter observed today. Understanding the geometry, dynamics, and composition of filaments and voids is essential for constructing accurate models of galaxy formation, large-scale structure evolution, and the interplay between dark matter, baryons, and cosmic expansion. In essence, cosmic filaments and voids represent the universe's skeletal framework, directing the flow of matter, shaping galaxy evolution, and preserving the imprint of the early universe's density fluctuations, providing a unifying structure that links the microphysics of baryons and dark matter to the grand architecture of the cosmos, revealing how the universe evolved from a nearly homogeneous plasma to a richly structured hierarchical system, clusters, and vast interconnecting filaments that define the observable universe today. Within the vast cosmic web, galaxies serve as the primary sites for star formation, transforming cold, dense clouds of gas into brilliant stellar populations that illuminate the universe and drive its chemical and dynamical evolution. Star formation occurs predominantly within molecular clouds, regions composed mainly of hydrogen molecules, dust, and trace amounts of heavier elements, where local density enhancements allow gravity to overcome thermal pressure and initiate the collapse of gas into protostellar cores. The process is regulated by a complex interplay of physical mechanisms including turbulence, magnetic fields, radiation pressure, and feedback from previous generations of stars, which can both trigger and suppress further star formation. Within these cosmic nurseries, dense cores condense under gravity. Heating as potential energy is converted into kinetic and thermal energy, eventually igniting nuclear fusion once central temperatures reach the threshold necessary for hydrogen burning. This marks the birth of a star, which subsequently evolves along a sequence determined primarily by its initial mass and composition. Star formation is often clustered, producing groups or clusters of stars that form nearly simultaneously from the same molecular cloud, leading to the creation of open clusters associations, and eventually bound globular clusters over cosmic time. The efficiency of star formation, defined as the fraction of gas converted into stars within a given region, depends on both local conditions and global galaxy properties, such as gas density, metallicity, and the presence of spiral arms or bars that compress gas and induce collapse. Feedback processes from young massive stars, including ultraviolet radiation, stellar winds, and supernova explosions, play a crucial role in regulating the interstellar medium, injecting energy, driving turbulence, and enriching the surrounding gas with heavy elements, which in turn influences subsequent star formation. Observationally, star formation can be traced through emission in various wavelengths, including ultraviolet, infrared, and radio, with infrared emission highlighting regions where dust absorbs starlight and re-emits energy, revealing deeply embedded protostars. Star formation rates vary significantly across galaxies and cosmic time, peaking during the so-called cosmic noon around redshift 2 to 3, when the universe experienced its most intense period of star formation and galaxy assembly. Understanding star formation is essential for interpreting galaxies, evolution, chemical enrichment, and the buildup of stellar mass, as stars are the primary engines of energy and heavy element production that shape galaxies and their environments. The initial mass function, IMF, which describes the distribution of stellar masses at birth, influences the chemical yield, feedback strength, and evolution of stellar populations, providing a critical link between microscopic processes in molecular clouds and the macroscopic properties of galaxies. Star formation is also closely tied to the dynamics of galaxies, with spiral density waves, bars, and interactions with neighboring galaxies enhancing or suppressing activity depending on the resulting gravitational and tidal effects. Numerical simulations incorporating hydrodynamics, magnetohydrodynamics transfer are indispensable for modeling star formation, allowing researchers to explore the effects of turbulence, feedback, and large-scale dynamics on the collapse of molecular clouds and the emergence of stellar populations. On cosmological scales, star formation in galaxies contributes to the reionization of the universe, the chemical enrichment of the intergalactic medium, and the evolution of cosmic luminosity density, connecting local processes within clouds to the history of the universe as a whole. The life cycle of stars from birth to eventual death drives the formation of planetary systems, the recycling of gas through supernova explosions, and the creation of compact objects such as neutron stars and black holes, linking star formation directly to the evolution of galaxies and the broader cosmic ecosystem. In essence, star formation represents the engine of cosmic evolution, transforming gas into luminous matter, driving chemical enrichment, shaping galaxy dynamics, and influencing the intergalactic medium, forming the backbone of observable cosmic history and as year, establishing the foundation for planets, life, and the emergence of complex structures within the universe. By studying the physics, efficiency, and environmental dependence of star formation, astronomers gain insights into how galaxies assemble their stellar content, how energy and metals are distributed, and how the universe evolves from the primordial conditions following the Big Bang to the rich, structured cosmos we observe today. Supernovae, the explosive deaths of massive stars, represent one of the most dramatic and influential processes in the evolution of galaxies, playing a pivotal role in regulating star formation, enriching the interstellar medium with heavy elements, and shaping the physical and chemical structure of galaxies over cosmic time. These cataclysmic events occur when stars exceed critical mass thresholds, such as in the case of Type II supernovae, arising from the collapse of massive stars' iron cores, or Type Y supernovae, triggered by thermonuclear runaway in white dwarfs accreting material from binary companions. The immense energy released during a supernova explosion, typically on the order of 10 circumflex 44 joules, drives shock waves through the surrounding interstellar medium, compressing, heating, and sometimes expelling gas which can either trigger the formation of new stars or inhibit star formation depending on local conditions. Supernovae are primary contributors to the chemical enrichment of galaxies, synthesizing and dispersing elements heavier than helium, such as carbon, oxygen, silicon, and iron, into the interstellar medium, providing the raw materials necessary for the formation of planets, complex molecules, and ultimately life. The interplay between supernova feedback and the interstellar medium shapes galaxy evolution in multiple ways, influencing gas dynamics, star formation efficiency, and the overall mass and structure of galaxies. Energy and momentum injection from supernovae can drive galactic winds, expelling gas from low-mass galaxies and regulating their growth while redistributing metals to larger scales, including the circumgalactic and intergalactic media. Observations across the electromagnetic spectrum, from radio to X-rays, reveal supernova remnants, expanding shells of ionized gas, and shock-heated regions that provide direct insight into the impact of these explosions on their host galaxies. Supernovae also generate cosmic rays and magnetic fields, influencing the microphysics of the interstellar medium and contributing to pressure support against gravitational collapse in molecular clouds. The frequency and distribution of supernovae depend on the initial mass function, star formation history, and environmental conditions within galaxies, with starburst regions and massive spiral arms typically exhibiting elevated supernova rates. Type Ia supernovae, in particular, serve as standardizable candles in cosmology. In cosmology, enabling precise measurements of extragalactic distances and the discovery of the universe's accelerating expansion, highlighting the intersection of stellar feedback and large-scale cosmic observations. Feedback from supernovae interacts with other galactic processes, including radiation pressure from massive stars, stellar winds, and active galactic nuclei, creating a complex network of influences that govern the regulation of star formation and the evolution of galaxies over billions of years. In addition to driving outflows and enriching the interstellar medium, supernovae contribute to the recycling of gas within galaxies, facilitating the formation of successive generations of stars with progressively higher metallicalities, thereby influencing stellar populations, planetary formation, and chemical evolution. High-resolution simulations of galaxies incorporate supernova feedback to reproduce observed galaxy properties, including morphology, star formation rates, and mass-metallicity relationships, emphasizing the critical role of these energetic events in shaping cosmic evolution. On larger scales, supernova-driven winds can influence the evolution of galaxy groups and clusters, transporting metals and energy into the intra-cluster medium, thereby affecting thermal balance, cooling processes, and the observational signatures of X-ray emitting gas. The study of supernovae also informs our understanding of compact objects, such as neutron stars and black holes, which are formed as remnants of massive stellar explosions, linking stellar feedback to high-energy astrophysical phenomena and gravitational wave sources. In essence, supernovae and the associated stellar feedback mechanisms are fundamental drivers of galaxy evolution, connecting the life cycle of individual stars to the global properties of galaxies and the intergalactic medium, shaping the chemical and dynamical state of the cosmos, and providing the energy and material necessary for subsequent star formation, planetary systems, and the emergence of life. By understanding supernova feedback, astronomers can trace the interplay between stars and their host galaxies, explore the regulation of star formation across cosmic time, and reconstruct the processes that have transformed the universe from a primordial expanse of hydrogen and helium into a richly structured, chemically diverse, and dynamically complex cosmos. Black holes, regions of space-time exhibiting gravitational fields so strong that nothing, not even light, can escape, and their energetic manifestations in the form of active galactic nuclei, AGN, represent some of the most influential and fascinating phenomena in the universe, shaping the evolution of galaxies and the intergalactic media. Supermassive black holes, typic, ally with masses ranging from millions to billions of solar masses, reside at the centers of most galaxies, including the Milky Way, and their growth and activity profoundly influence galactic dynamics, star formation, and the chemical evolution of their host galaxies. When these black holes accrete matter, gravitational energy is converted into radiation, often outshining the combined stellar luminosity of the entire galaxy, and giving rise to AGN, which include quasars, Seyfert galaxies, and radio galaxies, observed across the electromagnetic spectrum from radio to gamma rays. The accretion process forms a hot, dense disk of infalling gas around the black hole, generating powerful jets, and outflows that transport energy and momentum into the surrounding interstellar and intergalactic medium, regulating star formation and redistributing gas and metals. Feedback from AGN plays a critical role in galaxy evolution, suppressing excessive star formation in massive galaxies, shaping the morphology of galaxies, and influencing the thermal state of the circumgalactic and intra-cluster medium. Observations of AGN provide crucial insights into the growth history of supermassive black holes, the physics of accretion disks, relativistic jets, and the interaction between central black holes and their host galaxies. High-resolution imaging and spectroscopy from telescopes, such as Hubble Space Telescope, Chandra X-ray Observatory, and the James Webb Space Telescope have revealed the structure of AGN, including broadline regions, narrowline regions, dusty tori, and relativistic jets, providing constraints on models of black hole accretion and feedback mechanisms. The coevolution of supermassive black holes and their host galaxies is evidenced by empirical correlations such as the M-sigma relation, which links black hole mass to the velocity dispersion of the galactic bulge, suggesting a deep connection between central black holes and galaxy formation processes. On larger scales, AGN-driven outflows and jets inject energy into the surrounding medium, preventing runaway cooling of gas in galaxy clusters and influencing the assembly of large-scale structures. Black holes also serve as laboratories for extreme physics, allowing tests of general relativity, the nature of event horizons, and the behavior of matter under immense gravitational and magnetic fields. The detection of gravitational waves from merging black holes by observatories such as LIGO and Virgo has opened a new observational window, enabling the study of black hole demographics, formation channels, and their role in cosmic evolution. Supermassive black holes are thought to form and grow through a combination of direct collapse, accretion of gas, and mergers with other black holes, influencing galaxy evolution at all epochs and contributing to the observed population of quasars at high redshift. The radiation and mechanical feedback from AGN also drive chemical enrichment by distributing metals synthesized in the host galaxy across the intergalactic media, affecting the formation of subsequent generations of stars and galaxies. AGN variability, both in luminosity and spectral characteristics, provides insights into the dynamics of accretion flows, the structure of accretion disks, and the timescales over which black holes interact with their environment. In essence, black holes and active galactic nuclei are central engines of cosmic evolution, linking the microphysics of gravity and accretion to the macroscopic properties of galaxies, clusters, and the intergalactic medium, regulating star formation, distributing energy and metals, and shaping the structure of the universe over billions of years. By studying these cosmic powerhouses, astronomers gain insights into the life cycles of galaxies, the growth of supermassive black holes, and the mechanisms that govern energy and matter in extreme environments, revealing how these enigmatic objects have influenced the universe from its earliest epochs to the present day, and highlighting their critical role in the grand narrative of cosmic history. Galaxy evolution is the intricate process by which galaxies form, grow, and transform over billions of years, governed by the interplay of gravity, gas dynamics, star formation, feedback processes, interactions, and mergers within the expanding universe. Galaxies begin as small, irregular collections of gas and dark matter, forming stars and gradually assembling into larger structures through hierarchical merging, following the initial density fluctuations seeded during the early universe. Star formation within galaxies drives their chemical and photometric evolution, enriching the interstellar medium with heavier elements produced in stellar cores and dispersed by supernovae, thereby influencing the composition of future generations of stars and planetary systems. Morphological transformation is a hallmark of galaxy evolution, with galaxies evolving from irregular and clumpy systems in the early universe into well-defined spirals, ellipticals, and lenticulars, shaped by internal processes and external influences, such as tidal interactions, mergers, such as tidal interactions, and accretion of gas from the intergalactic medium. Observations of galaxy at dot. Different redshifts provide snapshots of their evolutionary stages, revealing trends such as the decline in star formation rate, from cosmic noon to the present epoch, the growth of stellar mass, and changes in morphology over cosmic time. Feedback from supernovae and active galactic nuclei regulates the rate of star formation, redistributing gas and metals, and preventing excessive accumulation of stellar mass, thereby influencing the overall evolutionary trajectory of galaxies. Galaxy interactions and mergers play a crucial role in their evolution, triggering bursts of star formation, inducing morphological changes, fueling central supermassive black holes, and sometimes transforming spiral galaxies into ellipticals or spheroidal systems. Environmental effects such as residing in dense clusters versus isolated regions significantly impact galaxy evolution. With galaxies in clusters often experiencing accelerated quenching of star formation due to RAM pressure stripping, tidal interactions, and suppression of gas accretion. The chemical evolution of galaxies, traced through spectroscopy of stars and gas, reveals the history of star formation, nucleosynthesis, and gas inflows and outflows, providing insight into the cumulative processes that shape a galaxy's metallicity and stellar population. Observational programs such as the Hubble Deep Field, Sloan Digital Sky Survey, and recent JWST surveys have extended our understanding of galaxy evolution to high redshifts, uncovering the properties of galaxies just a few 100 million years after the Big Bang, and mapping their growth over cosmic time. Theoretical models and cosmological simulations, including Illustris, EAGL, and FIRE, incorporate the physics of gas cooling, star formation, feedback, and mergers to reproduce observed galaxy populations, and explore the dependencies of evolution on mass and cosmic epoch. Galaxy evolution also encompasses the formation of galactic substructures, including bulges, disks, bars, spiral arms, and stellar halos, each reflecting the cumulative effects of internal dynamics, star formation, and external interactions. Dark matter halos underpin the evolution of galaxies by providing gravitational potential wells that dictate gas inflows, star formation efficiency, and merger dynamics, linking the microphysics of baryons to the larger-scale structure of the universe. Stellar populations within galaxies evolve over time, with massive stars contributing to chemical enrichment and energy feedback, while low-mass stars provide long-lived repositories of information about early star formation and metallicity conditions. Supermassive black holes and their associated AGN feedback influence the evolution of massive galaxies by regulating star formation, heating the interstellar medium, and shaping galaxy morphology, linking central black holes to global galactic properties. In addition to the internal and environmental processes, cosmic accretion of gas along filaments sustains star formation in galaxies over extended periods, feeding their growth and driving secular evolution. Galaxy evolution is thus a dynamic, multi-scale process that encompasses the formation, growth, transformation, and eventual quenching of galaxies, integrating processes from stellar physics to cosmology and connecting the early universe conditions to the diverse population of galaxies observed today. By studying galaxy evolution, astronomers gain insight into the physical mechanisms that govern star formation, structural assembly, chemical enrichment, and the interplay between galaxies and their environment, revealing the pathways by which the universe transitioned from simple collections of gas and dark matter into the complex, richly structured cosmos filled with galaxies, stars, and planetary systems that we observe in the present epoch. The process of cosmic chemical enrichment describes the gradual transformation of the universe from a primordial state dominated by hydrogen and helium into a chemically diverse cosmos, rich in heavier elements, or metals, synthesized in stars and dispersed through galaxies and the intergalactic medium. Following the Big Bang, the universe contained primarily hydrogen, 75%, and helium, 25% by mass, with trace amounts of lithium and beryllium, forming the simple chemical foundation upon which all subsequent elements would be built. The formation of the first stars initiated nucleosynthesis, producing heavier elements through fusion reactions in stellar cores, including carbon, oxygen, nitrogen, and elements up to iron, which were later dispersed into the surrounding interstellar medium through stellar winds and supernova explosions. Supernovae, particularly Type II supernovae from massive stars, played a crucial role in distributing these metals, enriching gas clouds that would give rise to subsequent generations of stars, while Type Ia supernovae contributed significant quantities of iron and nickel. Over cosmic time, The cumulative effect of successive generations of star formation and feedback led to increasingly metal-rich environments, altering the cooling efficiency of gas, star formation rates, and the physical properties of galaxies. Metallicity, the fraction of mass in elements heavier than helium, serves as a critical diagnostic of a galaxy's evolutionary history, star formation rate, and gas accretion and outflow processes, providing a window into both local and cosmic chemical evolution. Observations of stellar populations, interstellar gas, and high redshift galaxies reveal a gradual increase in metallicity over time, with early galaxies exhibiting low metallicities reflective of primordial conditions, and later systems showing enrichment patterns indicative of cumulative nucleosynthetic activity. The enrichment of the intergalactic medium occurs through galactic winds, outflows, and tidal interactions, transporting metals from star-forming regions into the diffuse cosmic environment, influencing the formation of new galaxies, the cooling of gas, and the chemical composition of subsequent generations of stars and planets. Elements heavier than iron, produced through neutron capture processes in supernovae and neutron star mergers, further diversify the chemical inventory, contributing to the formation of complex molecules and materials essential for planetary systems and life. Observations of quasar absorption lines, including the Lyman alpha forest and metal absorption features, provide insights into the metallicity of the intergalactic medium and the spatial distribution of metals across cosmic scales. Chemical enrichment also drives the evolution of star formation, as higher metallicalities enhance radiative cooling, allowing gas to fragment more efficiently into low-mass stars, while feedback processes regulate the availability of enriched gas for future generations. The study of isotopic abundances, elemental ratios, and chemical gradients within galaxies and clusters provides critical constraints on stellar nucleosynthesis models, star formation histories, and the timing and sources of enrichment. Cosmic chemical enrichment is intimately linked to the life cycle of galaxies, supernova rates, and the growth of large-scale structures, highlighting the steadiness of stellar evolution, feedback mechanisms, and cosmological processes. The enrichment of the universe ultimately sets the stage for the formation of planets, complex molecules, and biological systems, making chemical evolution a foundational aspect of cosmic history. Theoretical models and numerical simulations incorporating star formation, supernova feedback, gas inflows and outflows, and galaxy interactions reproduce observed metallicity trends and reveal the timescales over which chemical enrichment occurs across different environments. Additionally, cosmic chemical enrichment impacts the opacity, cooling properties, and radiative transfer of gas in galaxies and the intergalactic medium, influencing the dynamics and efficiency of subsequent star formation and the thermal evolution of cosmic structures. In essence, cosmic chemical enrichment represents the progressive complexification of the universe, transforming it from a simple hydrogen-helium mixture into a chemically rich cosmos capable of supporting planets, life, and the diverse structures observed today. It integrates the physics of nuclear reactions, stellar evolution, feedback, and cosmic structure formation into a coherent narrative of elemental synthesis and distribution, linking microscopic processes within stars to macroscopic evolution across galaxies, clusters, and the intergalactic medium, and providing a crucial framework for understanding the history, evolution, and ultimate potential of the universe. The epoch of cosmic reionization, a critical phase in the universe's evolution, culminated when the intergalactic medium transitioned from being largely neutral to fully ionized, marking the moment when the universe became transparent to ultraviolet light, and galaxies, stars, and quasars could shine freely across cosmic distances. This transformative period, which began roughly 400 million years after the Big Bang, was driven by the emergence of the first luminous objects, including population 3 stars, early galaxies, and accreting supermassive black holes, whose intense ultraviolet radiation ionized neutral hydrogen atoms, stripping electrons from protons and creating expanding ionized bubbles that gradually overlap to permeate the cosmos. Observational evidence for the completion of reionization comes from multiple sources. The absence of complete Gunn-Peterson troughs and high redshift quasar spectra, the measurement of electron scattering optical depth in the cosmic microwave background, CMB, and studies of the 21-centimeter hydrogen line, all of which indicate that by approximately 1 billion years after the Big Bang, the universe had become fully ionized. The end of reionization had profound consequences for subsequent cosmic evolution, including changes in the thermal state and pressure of the intergalactic medium, which affected the ability of gas to collapse into dark matter halos and form new galaxies, thereby regulating star formation in low-mass systems. Reionization also influenced the visibility of early galaxies, as the ionization state of the surrounding medium determined the transmission of Lyman alpha photons and other ultraviolet radiation, shaping the observational signatures of high redshift galaxies. The interplay between the sources of ionizing photons and the evolving intergalactic medium created a highly inhomogeneous environment, with regions of fully ionized gas coexisting alongside pockets of remaining neutral hydrogen until percolation completed the process. Numerical simulations of reionization, incorporating radiative transfer, gas dynamics, star formation, and feedback processes, have been essential for modeling the timing, topology, and duration of the epoch, providing predictions that can be compared with observatio NS of high redshift quasars, galaxies, and the CMB. The feedback effects of reionization also had lasting consequences for galaxy evolution, as the increased thermal pressure of the ionized intergalactic medium suppressed gas accretion onto low-mass halos, reducing star formation and influencing the hierarchical growth of structure. Furthermore, reionization played a key role in chemical enrichment by enabling supernova-driven winds from early galaxies to disperse metals into the intergalactic medium, contributing to the subsequent formation of metal-enriched stars and planetary systems. The timing and completion of reionization are sensitive to the efficiency of ionizing photon production, escape fractions from galaxies, and the clustering of sources, with ongoing research aimed at constraining these parameters through high redshift observations and sophisticated cosmological simulations. Studies of the 21-centimeter signal from neutral hydrogen offer a promising avenue for probing the spatial and temporal structure of reionization, potentially revealing the size distribution of ionized bubbles, the evolution of the ionization fraction, and the contributions of different sources over time. The completion of cosmic reionization represents a major phase transition in the universe's history, transforming it from a dark, neutral state into a luminous ionized cosmos, setting the stage for the formation of mature galaxies, clusters, and large-scale structures. Reionization links the physics of the first stars, galaxies, and quasars to the thermal and ionization history of the intergalactic medium, illustrating how early luminous sources shaped the observable universe and influenced subsequent cosmic evolution. Understanding the completion of reionization also informs models of galaxy formation, the buildup of stellar mass, and the evolution of large-scale structure. As the ionization state of the universe affects the collapse of gas, the efficiency of star formation, and the propagation of radiation through the cosmos. In essence, the universe fully illuminated by the end of reionization represents a pivotal milestone in cosmic history, connecting the emergence of the first luminous objects to the observable structures of today, revealing how the interplay of radiation, matter, and gravity transformed a neutral, dark cosmos into the vibrant, structured, and ionized universe capable of supporting galaxies, stars, planets, and eventually life. The study of this epoch continues to provide critical insights into the nature of the first stars, galaxies, and quasars, the physics of the intergalactic medium, and the processes governing the evolution of cosmic structure, making the completion of reionization a cornerstone in our understanding of the universe's early evolution. The formation of solar systems represents a fundamental process in cosmic evolution, transforming diffuse clouds of gas and dust into structured systems of stars and orbiting planets, moons, asteroids, and comets, ultimately creating environments capable of supporting life. Solar system formation begins within molecular clouds, dense regions of gas and dust that collapse under their own gravity, often triggered by external influences such as supernova shock waves, stellar winds, or gravitational instabilities. As the cloud collapses, conservation of angular momentum causes it to flatten into a rotating protoplanetary disk surrounding a central protostar, where material gradually accretes onto the growing star. While residual gas and dust within the disk serve as the building blocks for planetary formation. Within these disks, small dust grains collide and stick together through processes like coagulation and electrostatic interactions, forming larger aggregates known as planetesimals, which eventually grow into protoplanets through gravitational accretion and collisions over millions of years. The distribution of material within the disk, temperature gradients, and the composition of gas and dust influence the types of planets that form, with rocky terrestrial planets typically emerging in the hotter inner regions and gas giants forming in the colder outer regions, where volatile compounds can condense. Feedback from the central protostar, including stellar winds, radiation pressure, and episodic outflows, interacts with the disk, influencing the migration of planetesimals, the clearing of residual gas, and the final architecture of the planetary system. Observations of protoplanetary disks. In young stellar clusters using telescopes such as the Atacama Large Millimeter Submillimeter Array and the Hubble Space Telescope reveal structures such as gaps, rings, and spiral patterns, indicative of ongoing planet formation and interactions between forming planets and the surrounding disk. The chemical composition of the disk, including the presence of water, organic molecules, and refractory elements, sets the stage for the eventual formation of habitable planets and the potential emergence of life. Linking planetary formation to astrobiology. Planetary migration, driven by gravitational interactions with the disk or other bodies, can significantly reshape the architecture of a solar system. Explaining the presence of hot Jupiters, resonant orbital configurations, and eccentric planetary orbits observed in exoplanetary systems. The late stages of solar system formation involve the clearing of residual gas and dust, stabilization of planetary orbits, and the formation of secondary bodies such as moons, asteroid belts, and comets, often through capture collisions or fragmentation processes. The study of our own solar system, including isotope compositions of meteorites, lunar samples, and planetary atmospheres, provides a detailed record of the processes that governed its formation, offering a template for understanding the diversity of exoplanetary systems discovered throughout the galaxy. Theoretical models and numerical simulations incorporating hydrodynamics, thermodynamics, and gravitational interactions reproduce key features of planetary formation, including core accretion, disk instability, and the timescales over which protoplanets grow and migrate. The formation of solar systems is intimately linked to stellar evolution, as the mass, luminosity, and lifetime of the host star influence the thermal environment of the disk, the potential habitability of planets, and the long-term stability of orbits. Moreover, the delivery of volatiles and complex molecules via cometary impacts, asteroid collisions, and disk chemistry contributes to the chemical diversity necessary for the emergence of life, demonstrating the interplay between planetary formation, chemistry, and astrobiology. Understanding solar system formation is essential for interpreting the variety of exoplanetary systems observed, the distribution of planetary types, and the likelihood of habitable worlds, while connecting the microphysical processes of dust coagulation, planetesimal growth, and disk dynamics to the macroscopic outcomes of planetary architecture and habitability. In essence, the formation of solar systems represents a critical stage in cosmic evolution, linking star formation, protoplanetary disk physics, and chemical enrichment to the creation of planets and potentially life-bearing environments, illustrating how the processes initiated billions of years ago in molecular clouds continue to shape planetary systems, including our own, and the broader quest to understand the origin and distribution of life in the universe. By studying the formation and evolution of solar systems, astronomers and planetary scientists gain profound insights into the physical and chemical mechanisms that govern the birth of planets, the emergence of habitable conditions, and the interconnected history of stars, disks, and planetary systems across cosmic time. Planetary habitability refers to the set of physical, chemical, and environmental conditions that allow a planet to support life, encompassing factors such as the presence of liquid water, a stable climate, a protective atmosphere, essential chemical elements, and energy sources necessary to sustain biological processes. The concept of habitability is rooted in the understanding of Earth as the only known life-bearing planet, guiding the search for similar conditions on other planets within our solar system and beyond, including exoplanets orbiting distant stars. The presence of liquid water is considered a fundamental requirement for life as we know it, as it serves as a solvent for biochemical reactions, facilitates nutrient transport, and mediates energy transfer, making planets within the habitable zone, or the region around a star, where temperatures allow liquid water to persist, prime candidates for life. Beyond water, planetary atmospheres play a crucial role in habitability by regulating surface temperature through greenhouse effects, protecting against harmful ultraviolet and cosmic radiation, and sustaining cycles of essential gases such as oxygen, carbon dioxide, and nitrogen that support biochemical processes. Geological activity, including volcanism, tectonics, and magnetic field generation, contributes to habitability by cycling nutrients, maintaining atmospheric composition, and shielding the planet from stellar winds and cosmic radiation, while also regulating climate stability over geological timescales. Planetary mass and composition influence habitability, as sufficient gravity is needed to retain an atmosphere, maintain liquid water, and support tectonic processes, while the chemical inventory determines the availability of essential elements for life, including carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. Orbital dynamics and stellar characteristics further impact habitability, with factors such as orbital eccentricity, axial tilt, rotation rate, and stellar luminosity fluctuations affecting climate stability, seasonal variation, and the long-term persistence of favorable conditions. In addition to these physical and chemical factors, the evolution of life itself can modify planetary habitability, as observed on Earth where biological activity has significantly altered atmospheric composition, including the accumulation of oxygen through photosynthesis and the regulation of greenhouse gases. The study of planetary habitability extends to moons and icy bodies such as Europa, Enceladus, and Titan, where subsurface oceans, geothermal heating, or complex organic chemistry create potential environments for life even outside conventional habitable zones. Habitability also depends on planetary system architecture, including the presence of giant planets that can shield interterrestrial planets from excessive impacts or destabilize orbits, and the distribution of debris and small bodies that can influence the delivery of water and organics. Observational techniques, including transit photometry, radial velocity measurements, direct imaging, and spectroscopic analysis of exoplanet atmospheres, allow astronomers to infer conditions related to habitability, such as surface temperature, atmospheric composition, and the presence of water or biosignature gases. The concept of habitability is dynamic, recognizing that life may exist under a broader range of conditions than those found on Earth, potentially adapting to extreme temperatures, pressures, or chemical environments, expanding the scope of astrobiological exploration. Theoretical models of planetary climate, atmospheric evolution, and geophysical processes provide insights into the long-term stability of habitable conditions, enabling predictions of which planets and moons may maintain environments conducive to life over billions of years. Understanding planetary habitability also informs the search for extraterrestrial life, guiding missions such as Kepler Space Telescope, TESS, and upcoming missions like James Webb Space Telescope to prioritize targets with the highest potential for life detection. The interdisciplinary study of habitability integrates astrophysics, planetary science, geochemistry, atmospheric science, and biology, revealing the complex interactions that determine whether a planet can support life, from its formation to its long-term evolution. In essence, planetary habitability is a cornerstone of understanding our place in the cosmos, linking the processes of planetary formation, stellar evolution, geophysical dynamics, and atmospheric chemistry to the emergence and sustainability of life, providing a framework for identifying potentially life-bearing worlds, interpreting exoplanetary data, and exploring the fundamental conditions required for life throughout the universe. By studying habitability, scientists gain insights into the delicate balance of physical, chemical, and biological factors that have made Earth a cradle for life, while extending the search for similar conditions beyond our solar system, deepening our understanding of the potential distribution and diversity of life in the cosmos. The ultimate fate of the universe is one of the most profound questions in cosmology, encompassing scenarios that arise from the interplay of cosmic expansion, dark energy, matter density, and the laws of thermodynamics, with predictions ranging from eternal expansion to eventual collapse or heat death. Observations over the past few decades, including measurements of distant supernovae, the cosmic microwave background, and large-scale galaxy surveys, have revealed that the universe's expansion is accelerating, driven by a mysterious form of energy, known as dark energy, which constitutes roughly 70% of the total energy density of the cosmos. This accelerated expansion has profound implications for the long-term evolution of cosmic structures, as galaxies and clusters will recede from one another at ever-increasing velocities, eventually becoming causally distant regions of the universe. One possible scenario for the fate of the universe is the so-called heat death or big freeze, in which the expansion continues indefinitely. Stars exhaust their nuclear fuel, galaxies grow dark, and matter decays or becomes widely dispersed, leading to a cold, dilute, and entropy-dominated cosmos, devoid of usable energy for sustaining complex processes. In this scenario, the universe approaches a state of maximum entropy, consistent with the second law of thermodynamics, where all energy gradients are smoothed out, and no thermodynamic work or life-sustaining processes can occur. Another possible fate involves the Big Rip, a hypothetical outcome in which dark energy grows increasingly dominant and its repulsive effect intensifies, eventually tearing apart galaxies, stars, planets, and even atomic structures, culminating in a singularity where space-time itself is disrupted. Conversely, if dark energy were to diminish or reverse, the universe could enter a big crunch, wherein gravitational attraction overcomes expansion, causing a global collapse back into a hot, dense state reminiscent of the Big Bang, potentially followed by cyclic or bounce scenarios, depending on the underlying physics, the distribution of matter and dark energy, the geometry of space, and the equation of state of dark energy determine which of these outcomes is most likely, with current observations favoring a flat, accelerating universe that trends toward heat death. Cosmic evolution toward these fates involves stages including the exhaustion of stellar fuel in galaxies, the decay of stellar remnants such as white dwarfs, neutron stars, and black holes, the evaporation of black holes via Hawking radiation over extremely long timescales, and the dilution of baryonic and dark matter as expansion proceeds. The timeline for these events spans unfathomably long durations, from tens of billions of years for star formation to cease, to 10 circumflex 100 years or more for black hole evaporation, Heilig, hitting the immense scales over which cosmic processes unfold. The expansion and fate of the universe are also influenced by the interplay between gravity, dark energy, and cosmic structure formation. as the clustering of matter and feedback from galaxies and AGNs shape the large-scale distribution of matter and energy. Observational cosmology, theoretical modeling, and simulations allow researchers to explore these scenarios, examine the implications for the ultimate accessibility of matter and energy, and assess the conditions under which structures like galaxies, stars, and planets may persist or vanish. Beyond thermodynamic and structural considerations, the fate of the universe has implications for information, complexity, and the potential survival of life or intelligence, posing philosophical and scientific questions about the long-term prospects for existence in an expanding cosmos. In the distant future, even the radiation from the cosmic microwave background will redshift to undetectable levels, and the universe will become increasingly dark and empty, leaving isolated remnants in an otherwise cold and dilute space. The study of the universe fate unites fundamental physics, cosmology, thermodynamics, and astrophysics, linking the behavior of dark energy, the life cycle of matter, and Pyre 1, and the evolution of cosmic structures to predictions about the ultimate trajectory of all matter and energy. In essence, the fate of the universe represents the culmination of cosmic history, from the Big Bang through galaxy and star formation, chemical enrichment, planetary evolution, and the emergence of life, extending to a far future dominated by entropy, isolation, and expansion. By understanding these processes, scientists gain a framework for interpreting the long-term consequences of cosmic dynamics, the role of dark energy in matter, and the potential endpoints of structure and life in the universe, providing a profound perspective on the transient nature of existence and the ultimate destiny of all cosmic phenomena. The study of the universe fate not only informs astrophysics and cosmology, but also frames our understanding of time, energy, and complexity on the grandest scales, connecting the physics of the smallest particles to the evolution of the largest cosmic structures, and illuminating the pathways through which the universe may continue or conclude its remarkable journey from the Big Bang to eternity. Dark matter is a mysterious and invisible form of matter that makes up approximately 27% of the universe's total mass energy content. Although it does not emit, absorb, or reflect light, its presence is inferred through gravitational effects on visible matter, galaxy rotation curves, gravitational lensing, and the cosmic microwave background. Dark matter plays a critical role in the formation of galaxies, galaxy clusters, and large-scale cosmic structures, acting as a gravitational scaffolding that drives the assembly of matter. Understanding dark matter is central to modern cosmology, as it influences the evolution of the universe from the earliest density fluctuations to the structure we observe today. Its exact composition remains unknown, with candidates including weakly interacting massive particles, WIMPs, axions, and sterile neutrinos, making it one of the most compelling mysteries in astrophysics. Dark energy is the enigmatic force responsible for the accelerating expansion of the universe, constituting nearly 68% of its total energy content. Observations of distant supernovae, galaxy clusters, and the cosmic microwave background indicate that dark energy exerts a repulsive effect, counteracting the gravitational pull of matter. The nature of dark energy remains unknown, with theories ranging from a cosmological constant, Lao, to dynamic scalar fields or modifications of general relativity. Its influence determines the ultimate fate of the universe, dictating whether expansion continues indefinitely, accelerates toward a big rip, or slows down in alternative scenarios. Dark energy represents one of the most profound challenges for physics, cosmology, and our understanding of fundamental forces. Exoplanets are planets orbiting stars beyond our solar system, and the study of their diversity, composition, and environments is revolutionizing our understanding of planetary formation and habitability. Thousands of exoplanets have been discovered using transit photometry, radial velocity, direct imaging, and gravitational microlensing. These planets range from gas giants, super-Earths, and mini-Neptunes, to rocky terrestrial worlds, some located within their star's habitable zone. The search for biosignatures, such as atmospheric oxygen, methane, or water vapor, guides the quest to identify potentially life-bearing worlds. Exoplanet research bridges astronomy, planetary science, and astrobiology, opening a new era of exploration beyond our solar system. Studying the cosmos provides profound insights into humanity's place in the universe, revealing the interconnectedness of all matter, energy, and life. From the Big Bang to the formation of stars, galaxies, and planets, cosmic evolution offers context for the origins of Earth, life, and intelligence. Observations of distant galaxies, exoplanets, and cosmic phenomena expand our perspective, emphasizing the fragility and uniqueness of our planet. Astronomy, cosmology, and space exploration inspire scientific curiosity, technological progress, and philosophical reflection, challenging humans to explore, understand, and protect their place in the vast universe. By understanding the cosmos, we gain perspective on the past, present, and potential future of life and civilization.